Welcome to my presentation about adaptive localization in nonlinear ensemble transport filtering. My name is Max Ramgraber. I'm a current postdoctoral researcher at MIT. And in this talk, I want to present a new adaptation heuristic that can help us to find parsimonious, localized maps for nonlinear ensemble transport filters. To motivate this presentation, consider a classic problem we try to solve in filtering, in which we have a joint distribution of states and observations informed by previous data, which we now want to condition effectively on a new observation we have collected, indicated here as this gray vertical bar. And of course, in most cases, we won't be able to solve this in closed form, so we need ensemble-based methods that allow us to realize this update. And one of the most efficient and well-known methods to do so is, of course, the ensemble-Kalman filter, which realizes a very sample-efficient, powerful linear transformation that projects these joint samples onto the conditional, onto the posterior corresponding to the new observation. And this update works extremely well if the joint distribution is multivariate Gaussian, as it is in this instance. Unfortunately, this won't be always the case. For instance, if our forecast model is nonlinear, our observation model is nonlinear, or our noise or prior are in any way non-Gaussian, then our joint distribution might deviate from multivariate Gaussianity. And if we're very unlucky, it might look something like this. Now this here is of course some kind of made-up distribution where the underlying PDF follows some kind of spiral. But if we were to try to condition this distribution onto, say, this value, then it's perhaps unsurprising that the resulting posterior would not be Gaussian. It would be something very, very non-Gaussian. For instance, here it's clearly trimodal because we cut the spiral in 3 different locations. And if we were to take samples from this distribution and then just naively apply the ensemble-Kalman filter's update, it's perhaps unsurprising that this update could not give us the correct trimodal solution, because the linear projection the ensemble-Kalman filter relies on cannot generate these trimodal features on its own. So for these kind of distributions, we need something that's a bit more versatile and a bit more powerful. We need nonlinear updates. And there's a lot of different ways to do so in ensemble-based approaches. Particle filters are one approach, which are an extremely versatile way to make linear updates, but they're also quite sample inefficient. And in this talk, I want to advocate for the use of triangular transfer maps, which allow us to effectively generalize the sample-efficient update of the ensemble-Kalman filter, but particularly, they allow it to do something like this, where we take our joint samples and we still project them onto the conditional, but now we can do so in a nonlinear way, which, as indicated here, retrieves the trimodal posterior. And the method that I want to talk about in this presentation effectively helps us to find a parametrization for the map that is complex enough to capture the features of, well, hopefully any non-Gaussian distribution. So the key idea behind transfer methods is that we want to find a monotone and hence invertible map, a function that takes us from a complicated target distribution pi, which we might only know through samples, to a much simpler user-specified reference distribution eta, often a standard Gaussian. In our case, for example, in filtering, this target distribution would be this joint distribution between states and observations. And the reference distribution is just some random standard Gaussian distribution we have selected. Now, the hope is that once we have found this map, we can essentially approximate our unknown target distribution by transforming the reference into the target. And this then might help us to characterize these conditionals we want for filtering. Now, this process of transforming one distribution into another is effectively formalized by the change of variables formula, which is shown here on the bottom. And this allows us to derive an optimization objective whose minimization identifies a specific map that takes us from a specific target to a specific reference and back again. Now, the problem is that without further specification of this map, there are effectively infinitely many transformations that take you from one distribution to another and back again. So we narrow it down further by specifically positing that our maps are lower triangular, which looks a little bit like here, where the full map comprises of a number of map component functions, where the first map component function depends only on the first entry of the target vector, the second map component depends only on the first 2 entries of the target vector, and so on until the last map component function depends on everything. So every map component function depends on progressively more entries of the target vector. To make sure that the entire map is monotone, and hence invertible, we must also posit that every map component function must be monotone in its last argument. So S1 must be monotone in X1, S2 must be monotone in X2, and so on. And this structure has a number of really interesting properties. First off, the map is actually unique, which is very good for optimization. And it also turns out that these triangular maps are very easy to optimize, invert, which makes them quite attractive for computation. And they also have a very hidden property that helps us with conditioning, which we will see in the next few slides. So to understand why these triangular maps help us to characterize the conditional, to evaluate the posterior, the thing that we actually care about in data assimilation, we first have to understand how the forward and the inverse map works. Now assume that we have built our map, we have optimized our map, and now we want to evaluate the forward map, which takes us from the target distribution to the reference. Now in this case, we can effectively just evaluate every map component function independently, even in parallel, and then assemble the reference samples from the individual output of those map component functions. This is a quite straightforward operation. However, things get a lot more interesting if you take a look at the inverse map, which takes us from the reference back to the target. Now the inverse map can no longer be evaluated independently, but it must be evaluated in sequence, where we start by inverting the first map component function, a simple one-dimensional root finding problem with a unique solution due to monotonicity, which gives us x1, and this x1 then serves as a secondary input for the second map component's inversion, turning it again into a one-dimensional root finding problem, easy to solve, with a unique solution due to monotonicity, which gives us x2, and then x1 and x2 serve as inputs for the next inversion, again one-dimensional root finding, and so on over and over until we have inverted the entire map. And this dependence of each inversion on the outcome of previous inversions has a really interesting side effect, and that it effectively factorizes this complicated target distribution pi, the thing that we're interested in, into a product of marginal conditionals, where every single one of the terms down here is sampled by one of the map component inversions up here. And you might ask yourself, okay, that's all very nice. How does this help us with data assimilation, with conditioning? Well, as it turns out, we can manipulate this inversion process in order to sample from conditionals of the target distribution instead. So normally, if we were to just invert the map, we would solve this inversion from top to bottom one at a time. But if we want to sample conditionals, we can effectively manipulate this process by skipping the first few map component inversions and replacing the corresponding outputs, here x1 and x2, with values of our own choosing, say x1 star and x2 star. And if we then resume the inversion from the first map component function we haven't skipped, here s3, then we have all the ingredients we need, and we of course will no longer sample from the target, but we will sample from a conditional of the target, conditioned on those values we have provided. And in data assimilation, we would essentially arrange all our observations to be in the topmost blocks of a map and our states to be in the bottom blocks of a map. So we can effectively skip past the observations and use this conditioning trick in order to condition our states on observation values we have provided and measured from some kind of satellite or measurement device. Now, because this process might be a bit abstract in equation form, let's take a look at it visually. Here we want to invert a map from a reference distribution back to the target. The reference distribution, of course, is standard Gaussian, as we can see here in the top left. And if we want to transform these into samples from our target, in this case our spiral, then we need to invert our map, which here is two-dimensional. This means we have to start by inverting the first map component function on the top, which transforms the first marginal here on the horizontal axis and turns it into a marginal of a target distribution, x1. This then yields some kind of intermediate distribution, which serves as input for the second map component's inversion, which transforms the second marginal on the vertical axis and ultimately yields samples from the target distribution. Now, if you want to sample conditionals instead, we manipulate this process and we essentially skip the first inversion and make up our own x1 samples. For instance, here I've collapsed all the x1 samples onto a single numeric value in which I want to condition, which could, for instance, be a data point I've gotten from some kind of measurement device. And if we then just selectively apply the second map component function, pretending that we've already solved the first one before, then we of course no longer sample from a target, but we sample from a conditional of a target, conditioned on those values we have provided. And as we see here, this gives us the correct trimodal posterior we wanted to get earlier. Now this is already a very, very nice ability to have, but maps actually have a number of other really interesting properties that make this conditioning operation even more efficient. One of them is that maps actually make it very easy to exploit conditional independence. And this helps us to build extremely powerful localization structures directly into our update. So to understand this, let's recall again that every map component inversion corresponds to one of these terms in a factorization of a target distribution. Now, in many systems, we might actually have conditional independence properties, which would allow us to drop some variable dependencies from those terms in a factorization. And maps make it very easy to realize this effect by just dropping the corresponding variable dependencies from those map component functions. And this is very attractive for two reasons. The first reason is that this removal of variable dependencies builds conditional independence information directly into the update itself. And any kind of statistical information we can enforce by construction is information that we do not have to learn from samples, which makes our entire method a bit more robust and more reliable. The second advantage is that exploiting conditional independence this way, for obvious reasons, makes our map component functions numerically simpler, easier to evaluate, easier to optimize, which theoretically allows these methods to scale to really high-dimensional systems, provided that we have enough conditional independence. Now, the big problem here, of course, is that in most systems, we might not know the conditional independence properties, or conversely, we might not know which variable dependencies in those map component functions we have to keep. A very important question that we haven't talked about yet is what these map component functions that make up a triangular map actually look like. And in practice, we have a lot of different choices in how we parameterize these map component functions. A very common choice, for instance, is to use separable maps, in which the map component function basically just comprises of a number of potentially nonlinear terms, G and F, each of which takes one of the arguments of map component functions as its input. And we can separate these terms into two different classes. The first one are these G terms, which are non-monotone terms that depend on any input argument except the last one. And these G's, for instance, could just be combinations of some kind of non-monotone basis functions. For instance, here we have used Hermite functions, which are just Hermite polynomials with a Gaussian weight term that pulls the tails back to 0. And each of these basis functions, of course, is endowed with a coefficient, which are the things that we actually optimize in order to find a specific map linking the specific target to a specific reference. The only term that's special is the F term that depends on the last argument of a map component function, which must be monotone to ensure that the entire map remains monotone and hence invertible. And one way to guarantee this, for instance, is to use just combinations of monotone increasing basis functions, such as linear terms, error functions, soft plus functions, and so on. And then, of course, we have to constrain the optimization objective over the coefficients of these basis functions to make sure that they are positive and hence maintain the monotonicity in the last argument. But a very important decision we have to make here is how complex we actually make these basis functions, these terms G and F. To what order of polynomials do we go in G? How many error functions do we add in F? And so on. And if we keep these terms simple, for example, linear, then we would retrieve the ensemble Kalman filter as a special case. And as we make them more complex and more nonlinear, the map gains a greater ability to capture non-Gaussian features. But of course, the price for this is that the bias variance trade-off might become unfavorable. So finding the correct degree of complexity is a very important thing to keep in mind for these triangular maps. So behind these two questions, I think, lies the true potential of the triangular transfer maps. And this is basically that triangular maps can be extremely finely tailored to the demands of a system. So basically, we can build an filter, an ensemble transport filter, which uses the ensemble Kalman filter's efficient linear update almost everywhere and only becomes nonlinear where it really matters. And at this, we can even finely tailor the map to capture specific complex dependencies between variables in one system. And at the same time, we can build localization information directly into the update itself, which taken together means that these maps have fantastic potential for efficient nonlinear data assimilation. The challenge, of course, is that all the freedom in the world doesn't really help us if we don't have the information required to inform the decisions we have to make. And this is, I think, where map adaptation strategies come in, which help us to automatically shape the map to the demands of a system, and hence identify parsimonious maps that meet the demands of a distribution while respecting the information we have about it. Before we take a look at the first adaptation strategies, let's first set up a little bit of visual notation that will help making the next steps a little bit easier to understand. So what you see here on the right side is effectively a way to represent the structure and complexity of a triangular map, where basically every row corresponds to one map component function, and every column corresponds to a potential dependence of each map component function on each of the input variables in the target vector. So we see that the eponymous triangular structure of a map emerges quite naturally, where S1 can only depend on X1, S2 can only depend on X1 and X2, and so on. And the color and numbers over here effectively represent the level of complexity, the level of nonlinearity with which each map component function depends on each input variable. For instance, what we see over here is basically the simplest viable triangular map we can build. It's an identity map in which every map component function just depends linearly, order 1, on its last argument and on nothing else. And if we have standardized our samples before we apply the map, then basically this identity map does nothing. It basically just gives us back the target samples instead of transforming them to a reference distribution. Of course, we can also represent more complex maps this way. For instance, what you see over here is a nonlinear sparse map, where, for instance, this fifth map component function here could theoretically depend on all input arguments from x1 up to x5. But in fact, this one only depends on x2 and on x5. And specifically, it depends with a level of complexity of 3 on x2 and the level of complexity of 2 on x5. And what these levels of complexity mean is effectively left to us. So commonly, a level of complexity of 0 means there's no dependence. A level of complexity 1 might mean a linear dependence. And then the higher the complexity, the more nonlinear the map becomes. For instance, this G term of order 3 could mean that we use Hermite functions up to order 3. Whereas a complexity level of 2 in x5 could, for instance, mean it's a linear term plus a single error function. And the basic idea is that the higher the complexity, the more nonlinear this dependence becomes. And with this, let's take a look at the first adaptation algorithm we have developed. That's basically the EnSing algorithm that's been developed by Ricardo Baptista, Rebecca Morrison, and Yusuf Marzouk. And in a very, very small nutshell, how this algorithm works is that we start with a very simple map, originally just the identity. And then we go for a number of iterations, where at every iteration, we add a number of candidate terms, which we can conceptually think of as increasing the complexity of every block in this representation by 1. The real algorithm has a bit more nuance to this, but to keep it simple, let's think of it this way. And then for every one of these proposed basis functions, we evaluate the gradient of the optimization objective, and then select the candidate term with the steepest gradient in the optimization objective for every map component function and add them to the map. And then we keep iterating over the steps over and over again until we have decided that the map is sufficiently complex. Now, this algorithm is pretty straightforward and it's pretty powerful, but if it is one drawback, it's at this second step here. This second step has to look ahead at a significantly more complex map, basically evaluating a number of candidate functions, most of which we discard, in order to decide where we make the map more complex. Now, this is fine in small and even moderately dimensional maps, but if we go to high dimensional settings, or we go into systems in which efficiency is key, for instance, data assimilation, where we have to optimize a lot of maps, then we might want to switch from this to something that might be more computationally efficient. So what this talk is basically about is an attempt to replace the steps in the middle with something that's a bit more efficient at the cost of being a bit more approximate. Now, that's of course a little bit tricky because the steps we replace serve a very specific purpose in the adaptation algorithm. Mainly, they inform the adaptation procedure. And effectively, they do so in a very, very natural way by basically just trying what every candidate term does before it's added to the map. And that's, of course, a little bit inefficient. So in our strategy, we thought maybe alternatively, we can inform the adaptation strategy in a different way. And towards this end, we exploit the fact that we actually know what the output of a sufficiently complex map should look like. It should be standard Gaussian, but if our map is still too simple, then its output might deviate from standard Gaussianity in some ways. And as it turns out, there's a really interesting correspondence between a scatter plot matrix of a map output and this block structure of a map that we've introduced before. So what you see over here, for instance, is the map output of an identity map applied to a spiral target distribution. And what you see, of course, here in the scatter plot matrix is that over here you see the horizontal marginal of this map output. Here you see the vertical marginal of a map output. And here you see the joint distribution between these two marginals, the spiral. And of course, if our map is just an identity map, then it doesn't really transform the distribution. It just gives us back our target distribution, which obviously is quite far removed from standard Gaussianity. But as it turns out, if we increase the complexity of the diagonal terms in the map, for instance, this one over here, the map gains the ability to transform this marginal into something that's closer to standard Gaussian. So, for instance, if we illustrate this here, making this map component functions, this term more complex, it transforms this part of the map into something that's, well, standard Gaussian. And likewise, if we increase the complexity of this block over here, this diagonal block, then it transforms the corresponding marginal in the top left into a standard Gaussian marginal. Now, if we were to only restrict our attention to the diagonal blocks, then this essentially gives us a map output that's marginally Gaussian, but it's still not standard Gaussian, because the samples here are still coupled by something that's very much not independent. So basically, just focusing on the diagonal terms is something you can think of as Gaussian anamorphosis. And of course, unraveling this dependence is something what the off-diagonal terms are for. So if we increase the complexity of those, then they basically decouple the marginals in the corresponding row and column. So that's the task of the off-diagonals. And if the map is of sufficient complexity, as it is here, then we get standard Gaussian map output. So the idea that we had is that effectively we can use this correspondence between the scatter plot matrix and this block representation of a map in order to decide where we have to make the map more complex. And for this, of course, we need two types of tests. The first is a test that determines how independent these off-diagonal terms are. And the second one is a test that determines how Gaussian these diagonal terms are. And for this, there's a lot of choices we can make. For the Gaussianity test, for instance, we could use the Kolmogorov-Smirnov test or the Shapiro-Wilk test. But we specifically use the likelihood ratio test, also known as the G test, in which we take our marginal samples and then we first apply a standard Gaussian CDF, which maps the samples onto the unit interval between 0 and 1. We then separate these samples into a number of bins, for instance, 3. And then we can calculate the G-test statistic, where basically the histograms we get from step 3 serve as the observed histograms in the likelihood ratio test. And of course, as any kind of hypothesis test, we need a null hypothesis. And this is the E subscript I over here, which is, in our case, the null hypothesis of standard Gaussianity, which effectively results in uniform histograms, which you can, of course, calculate in closed form. The test for independence is a little bit more complex, where we take our bivariate marginal, the one that corresponds to a row and column of the marginals, and we apply a standard Gaussian CDF to both of the dimensions, which maps the samples onto the unit interval, again, between 0 and 1, in 2 dimensions. And once more, we separate this interval into a number of bins, here in 2D, and we count the samples in each bin to get our observed histograms for the likelihood ratio test. Now again, if you want to apply the G-test, then we need a null hypothesis. And in this case, our null hypothesis is independence. So towards this end, we first determine the marginal histograms of our samples by basically summing the samples in each direction and determine the counts in each bin. And if we then take the outer product between these marginal histograms, we effectively separate them into the individual 2D bins and get our expected histograms under the null hypothesis of independence. And then we can calculate the G-test statistic, where we get our observed histograms from step 4, and we get our expected histograms from step 6. And for both the Gaussianity test and the independence test, we can threshold this G-test statistic with the chi-squared distribution, where the degrees of freedom depends on the number of bins we have. So this brings us back to our adaptation algorithm, where we replaced the expensive exploration of basis functions basically by just analyzing the output of a scatterplot matrix of a map. The scatterplot matrix of the output of a map, this way around. And we calculate the deviation from the null hypothesis for each of these entries in the scatterplot matrix, and then just make the map more complex in the corresponding blocks. And we keep doing this until either all null hypotheses are fulfilled, or we reach a maximum level of map complexity. So with this, let us take a look at an actual example where we apply this for nonlinear ensemble transport filtering. In this example case, we used Lawrence 96, which is a very common test case, which has commonly 40 states, which live on a periodic domain, sort of on a circular domain represented as this ring over here. For certain choices of forcing, this system is chaotic. And this might be a bit of a hot take. Despite its nonlinear and chaotic nature, Lawrence 96 is actually a pretty lame test case for nonlinear filtering, because as it turns out, the joint distributions we get are actually very close to Gaussian, which means that the ensemble Kalman filter, a linear filter, is pretty close to optimal. So why did I use this test case if it is so boring? Well, because as it turns out, it has a very, very nice localization structure. Because the states live on this ring, if you observe one of these states, basically the filter only has to update maybe 6 states to either side, and that should be fine. So we want to see here if our adaptation algorithm can automatically detect this localization structure and if it can exploit it as well. And at the same time, we also want to see if a filter notices that the system is pretty close to Gaussian, so it doesn't require two nonlinear maps. For a data assimilation problem, we assume that we observe every second state, and we assume that the observation errors are independent of each other, which by extension also means that all of the observations are conditionally independent of each other, given all of the states. And this effectively allows us to assimilate the observations one at a time, where we essentially start by assimilating the first observation, updating the states, then we move to the next observation, we assimilate the next observation, we update the states, we move to the next observation, we assimilate the next observation, we update the states, and so on until we have assimilated all 20 observations. And this might seem like a pretty roundabout way of realizing the update, because instead of just one data assimilation update, we now have 20. But as it actually turns out, assimilating the observations this way improves performance quite a bit, because first off, we can use simpler and sparser maps to make all of these individual updates. And a second advantage is that this essentially enforces the conditional independence between the observations by construction, which makes the entire algorithm less prone to spurious correlations. And this again mirrors this thing we've mentioned before, where it's always better to enforce statistical information by construction than to hope that we get this out of the samples by itself. So this also leads to lower root mean square errors. Now, of course, an important question we have to make, decision we have to make if we want to use maps for inference, is that we have to decide how we arrange our states and observations. Now, of course, we want to use the conditioning trick in order to update the states. The observation must be at the top of the map. We might recall from the conditioning trick we mentioned earlier. And then we arrange the states basically in distance, based on distance from the observation, where we put the corresponding state in the second block of the map component function, its neighbors to the left and right in the third and fourth, the neighbors of this in the fifth and sixth, and so on. And in total, we go 10 states to either side to make sure we have plenty of space to find the localization structure. Yeah, and with this, we can take a look at some of the results we have made. So what you see over here is the ensemble mean root mean square error for an ensemble Kalman filter for different ensemble sizes plotted on the x-axis. The color of the scatter plots basically indicates that we have repeated this experiment for 10 different localization radii from 1 to 10, and have plotted the best localization radius for each ensemble size. And we can see a bunch of really interesting things here already for the ensemble Kalman filter. So of course, for small ensemble sizes, RMSEs are relatively large because we get a lot of spurious correlations. And as ensemble size grows, RMSEs drop until at the level of about 375, we can no longer get meaningful improvements with the ensemble Kalman filter because we are pretty much at the limit of what a linear update can give us. A second really interesting thing is that ensemble size grows, the localization radius also grows. So for small ensemble sizes, the spurious correlations are so strong that they actually degrade the performance of a filter. And as the ensemble size grows, we can afford larger and larger localization lengths, which update more and more states with every observation and improve performance. Compared to this is the result that our nonlinear adaptive ensemble transport filter gives us. And we can already see some really promising features here, despite this being some quite preliminary results. So we see that for ensemble sizes of 100 and larger, the map is actually very close to the performance of the ensemble Kalman filter. But as ensemble size grows, it starts to outperform the ensemble Kalman filter because it is not limited to linear updates, and it can in fact realize nonlinear updates. For ensemble size of 50, our adaptation algorithm is off to a magical adventure. I'm not quite sure what it does here, but it's still some quite preliminary results, and I hope to improve this later on. As I mentioned before, Lawrence 96 is a pretty lame test case, so actually the RMSE improvement here isn't that great. And if you plot as a reference, these are the results we got for a really manually optimized map, where we have used the optimal level of complexity and optimal level of localization, and we used inflation and we used regularization. So this uses the full bag of tricks, more than we used for either the ensemble Kalman filter or the adaptive EnKF. But we can see like the best RMSEs we get are still pretty close to the RMSE, maybe 0.1 better. So again, Lawrence 96 is a bit boring. But for 1,000 samples, we get pretty close to this optimum. It's also really interesting to take a look at the map that the adaptation algorithm actually proposes to use. So this is the map for the assimilation of the first observation. And we can see over here already really interesting patterns as the ensemble size increases. So we can see that as the ensemble size decreases from 50 to 1000, the adaptation algorithm proposes to use increasingly more nonlinear maps. So for small ensemble sizes, it still uses maps that are effectively linear, and only when the ensemble size gets large enough, it really starts to use nonlinear maps, which makes a lot of sense, because for small ensemble sizes, obviously we don't want to have massively nonlinear maps. The checkerboard pattern you see over here effectively comes from the fact that we arrange our states alternating from left to right. And so, these states are very far removed from each other on different opposite sides of the ring, almost. Another really interesting thing to look at is that these maps actually, the maps change from the first observation assimilation to the second observation assimilation. So this is for an order of 1000. Oh, sorry, I forgot one important thing to mention. Another really interesting thing for these maps is that the degree of nonlinearity decays a lot away from the diagonal, which also makes a lot of sense, because states, so blocks that are close to the diagonal, tend to be close to each other. And as we go away from the diagonal, the states are farther removed from each other on the ring, which means that the joint distribution between them gets simpler, closer to independence. And the adaptation algorithm detects and exploits this information, actually starts using less and less nonlinear maps until it eventually just basically uses order 0 maps and localizes these dependencies away. So this makes a lot of sense. Another really interesting thing, as you mentioned, is that this is the map for the assimilation of the first observation. And if you take a map for the assimilation of the second observation, it looks almost the same, with the difference being this block here, which is this row and this column, which has suddenly become a little bit simpler to the previous one. And this had me a bit stumped when I first saw this. But as it turns out, this block basically corresponds to this state that we've previously updated, which has made its marginal distribution simpler. And the adaptation algorithm actually has recognized and exploited this information. And if we go to the map for the third update, then actually we find this in two locations. Once here for the state we've just updated, and once here for the state we've updated before this. And so if we compare the map for the assimilation of the first observation to the map for the assimilation of the last observation, we can see a significant difference in the complexity of the map that we use. So the adaptation algorithm really seems to find extremely parsimonious maps. And I believe that analyzing these maps can reveal a lot of really interesting insights into the system and the nature of the updates. So I think this is value on its own, aside from the RMSE that we get. So this brings me to the summary. So in this presentation, we have introduced and discussed an alternative map adaptation strategy, which analyzes the output of a map in order to decide where it makes the next adaptation step. And while this is still a work in progress, the preliminary results are still very promising. So we find that both complexity and localization scale in a very intuitive and meaningful way with ensemble size. So it really seems quite promising that these adaptation algorithms can help us to find efficient and parsimonious nonlinear maps. And we've also seen that if RMSEs are large enough, then we get pretty close to the optimal maps that transport maps can give us, without the need for fudging around with regularization or inflation values. For moderate ensemble sizes, it still finds parsimonious maps and matches the complexity of the ensemble Kalman filter as well. Avenues that we still have to explore are, we want to play around with different thresholding. So thresholding, of course, decides when we decide something is sufficiently Gaussian or sufficiently independent. And exploring different values for this might improve performance even further. And another thing that's important to discuss is that here we have prescribed a very efficient variable ordering for localization, both for our adaptive map and for the EnKF. But as it turns out, this ordering can have big effects on the level of complexity of localization structures that we can exploit. And there are, in fact, algorithms that can help us to automatically find such an optimal ordering. This didn't fit in this talk, but the poster that belongs to this presentation discusses this in a little bit more detail. And with this, I want to thank you for your attention. If you have any kind of questions about this presentation, feel free to contact me via email or talk to me at some kind of conference if we meet.